second presentation of this morning. I welcome to the stage Mr. János Kepics.
Thank you. I will wait for a second to get the people in. So, hi everyone. My name is János Kepics. I study electrical engineering at BME, and I work at Bosch with scholarship, for which my project is Bluetooth Low Energy Security. And in this talk, I will give a presentation about this topic. So, as you may know, Bluetooth is everywhere we look. We have smart watches, smart locks, smart home surveillance cameras, but also it's not just in the consumer industry. It is also in the automotive sector and also in the medical industry too. Therefore, securing this protocol should be very important for us. A current attack was done on the Tesla. This was a BLE key application man-in-the-middle attack. So the attacker could perform this attack by exploiting GET messages sent to the Tesla key. This just shows that Bluetooth Low Energy Security should be very important for us, also working in the automotive field. But actually, when we talk about Bluetooth, this protocol includes two protocols, the Bluetooth Classic and Bluetooth Low Energy. Bluetooth Low Energy has a much slower data rate, but it consumes much less power. Therefore, most IoT devices use this protocol. I will give a short overview on the Bluetooth Low Energy stack. So, application programmers. So, you can separate this stack into three sections: the application layer, the host layers, and the controller layers. Most Bluetooth Low Energy application programmers interact with the application layer and some host layers. These are mostly the GAP, the GET, and the SMP layers. GAP generic access profile handles discoverability and connectability to a device. GET, the generic attribute protocol. This defines services and characteristics for an application. So, for example, there is the heart rate service, the HRS, with characteristics for monitoring your BPM. So, this characteristic and service is mainly used in smartwatches, for example. And also, there is the SMP, the security manager layer, which secures your connection. But as you may know, that there are controller layers, the link layer and the physical layer too. This gets developed by the IC manufacturer and the vendor supplier. Therefore, not much attention is added to these protocols by the application developers. So that's one reason we should focus on this. Here is how a link layer message exchange diagram looks like between a central and a peripheral device. So first, the peripheral device sends out an advertisement message, and then the central device can respond to this with a scan request message. Therefore, and then the peripheral device responds to this with a scan response. Therefore, both devices know of each other. And if the central would like to initiate a connection, it sends out a connection request message. After that, the two devices are connected, and the central becomes the master, and the peripheral becomes the slave. After this, the central device can change parameter needs of the connection with the parameter requests. Then the connection is secured with SMP messages. This is called pairing. And then get services and get characteristic messages can be exchanged. I would also like to mention that there are these type of attacks for wireless protocols. Eavesdropping, man-in-the-middle, relay replay attack, and DOS, so denial of service. In this talk, I won't go into much detail about it, but I think it's needed to mention that there are these type of attacks for which we should do security testing. One of the most efficient testing methods is fuzzing, so fuzz testing. In fuzzing, we send out random data and check for failures in the device. With this test, we check for the device's robustness, so can it handle unexpected data without a crash, and its security. Is it secure against buffer overflow, crashing, or deadlocking? Fuzzing structure looks like this. Firstly, there is the message generator part, where random data is generated. We used our own Fuzzing Engine, which I developed on top of a Bluetooth Low Energy framework. And then the message, the random message is passed to the message publisher, which sends out the data to the device under test. Then we monitor this device with target monitor, which can involve loggers, keep alive scripts, or health checks. So why would we like to fuzz link layer? You already saw this link layer exchange diagram, and you may have noticed that after and before the pairing, there isn't really any security measures implemented. Therefore, this should be focused on by our side. And these messages were link layer messages. Also, most fuzzer tools don't go down to this layer because, as I already mentioned, this layer is developed by the manufacturer and not the application developer. And other research projects were successful in corrupting link layer message exchanges. So these are the messages I fuzzed. There is a scan request message, connection request, and other parameter request messages. This test suite has been designed to act as a malicious link layer central device that sends out invalid requests to the tested link layer peripheral device, and we monitor the root with target monitors. Here is, so I already said that we use our own fuzzing tool, the Fuzzing Engine, which has a smart random data generation. This means that it has weights added to the different fields, and it uses seeding, so we can reproduce the random data. And on top of this, I developed the Kepics framework, which wraps the random data into a generic link layer message. You can see it there. So first there is a preamble, then the access address, then a PDU and the CRC. We fuzz the PDU because the other three fields are necessary to be correct to keep up the connection. So firstly, we choose what message we would like to fuzz. Then we choose what field to fuzz, and then what method. Then we can apply correction methods to this. To illustrate this, here is an example. So here, the first stage is choosing the message. You can see that each message has an added weight to it. It chose the connection request because it was, I guess it was more likely to be chosen because the weight was 0.2 of this message. The length request, for example, had a 0.1 weight added to it. And in the second stage, the fuzzing tool chooses what field it would like to fuzz. it chose the PDU type, and then it chooses the method. It chose the change value to maximum method. And then this random data created by the engine is passed to the message publisher, which was a Nordic device, the NRF52 dongle. This dongle was also used by the Ubertooth project, which had much success, and they created a special firmware for it, which can send out link layer messages created by Python code. Then we send this message to the target, and we monitor it. I implemented the file logger and the terminal logger, and in the first step of the fuzzing, we initialize the root, which means terminating connections from previous tests and connecting to the device. After that, we create the random seed and start the fuzzing process on a message. Then, during the fuzzing process, health checks and keep alive scripts are done. Health check uses the fact that in the specification, it says that in a connection phase, the device and the slave has to exchange empty PDU data type messages periodically, so we can monitor this message to see if the connection is still there. For the keep alive script, we also firstly run a health check, and if the health check is passed, then we don't have to do any keep alive script. But if it is failed, then we should reconnect to the device if it is reconnectable and it hasn't crashed yet. Here is a demo. I think it should be playable. So here is how okay, so here, this is how the terminal looks during the fuzzing process. With pink, you can see the keep alive scripts, and with yellow, you could see the health checks. I think this is quite buggy, but you can see the main part that it is sending out random messages to the device. And what were the lessons during this fuzzing process? We tested this fuzzing tool on 3 devices, smart lock, smart light bulb, and iTag. 2 of them crashed, which meant that you had to take out the battery and reinsert it to be able to connect to the device, or even send advertisement message from the peripheral device. And one of them deadlocked, which meant that the device stayed in a connection state after terminating the connection from our side, so it couldn't recognize that the connection should have been dead at that point. We can protect other devices by adding further security. This could mean adding a random Bluetooth address or securing the pairing process, but actually these findings should be reported to the Bluetooth SIG, and you should talk to your vendor supplier because, as I have said, this link layer is implemented by the manufacturer, the IC manufacturer, and this problem is actually on their side mainly. Further developments will be making our device stateful because Bluetooth Low Energy is a stateful protocol, and having more specific feedback added to the system will be also a priority, and also making it AI-based would be cool too. And a bonus topic is that in the previous, my previous topic at Bosch was eavesdropping on Bluetooth Low Energy data with an SDR, which is software-defined radio. This means that everything in the radio after the receiver is implemented by the software. I used the general purpose software-defined radio, which you could get for, I think, $80 on the market. It was a Pluto SDR, and I eavesdropped on advertising data on the 2.4 gigahertz band. And you can see in the right that I could capture the packets distinguishably from the noise, which I think is really interesting because this is a cheap device and you can implement the software for it in GNU Radio, which is block-based, so you don't even have to know programming languages for it. And if you have any questions, please ask them, and thank you for listening.
Any questions from the audience? We have a taker.
First of all, thank you for the presentation. And my question is, you said that you crashed 2 devices, and did you find anything that can be used to break, for example, the firmware of the device or something like that?
Can you repeat it, the last part of the question?
Did you find anything when those devices crashed that can be found, that can be used to break, for example, the firmware of these devices?
As I mentioned, the feedback to, so this is an embedded system, so making the feedback part of the fuzzing tool is not as simple as, for example, in other IT general purpose fuzzing tools. So this is also a working topic to have, to add more knowledge. After we actually know that something is crashed, we should also analyze with why it crashed. So actually we are now working on this. And so for now, the only thing we know that is that the link layer was corrupted, and we are currently working on analyzing this.
Okay, thank you.
Anybody else?
Was the smart lock you mentioned crashed or deadlocked?
Both.
Both?
Yes.
And if such a device gets crashed or deadlocked, is it possible to open it anyway without breaking the lock physically?
The deadlock, so the lock had a mechanism that if you try to, so it has a battery, and if you try to charge the battery, the connection gets lost instantly. So that was its reset mechanism, its hard reset. So we could reset the smart lock like that, but other ways it couldn't be unlocked. So you had to make a hard reset to unlock it.
Thank you.
Time for one more. I think that's it, János. Thank you for your excellent presentation this morning. If you can give him a round of applause.
Thank you.